So we'll finish off by taking a brief look at reductions to linear programming problems. So first of all is the idea of reducing to the standard form. When we first posed the Brewer's problem, we did it in terms of inequalities, and there's all sorts of different versions that you might imagine are more convenient for different types of problems with fewer restrictions. So as we've talked about, there's easy ways to deal with each of them. The standard form is not that different than the types of things people might want to do. So one thing is maybe somebody wants to minimize. So if somebody wants to minimize, you replace that minimization with the standard form says maximize, so you just negate everything. So that's equivalent. If you have inequalities, add a slack variable. Subtract the slack variable. It's got to be positive. That converts a greater than or equal constraint to an equality just by adding a variable. And if you have variables that are supposed to be unrestricted, just replace it as the difference between two variables that both have to be positive. So those are just examples of taking a non-standard form and reducing it to a problem that's in the standard form. For any particular problem that we might want to come up, then we can use these less restrictive non-standard, knowing that it's easy to for the LP solver to do the reduction from our non-standard form to the standard form. And certainly that's something that the solver can do for us. So actually, I didn't mention at the beginning, is why is it called linear programming? We're used to programming, that's say write Java code to solve a problem. But you have to remember, this is 1947. That's actually well before computers came into use and people were writing programs to do this stuff. Actually, for a small number of variables, you can basically solve it by hand. So what they meant by programming was more what there was another term used called planning. And so that was more take your problem and put it into a form that we can solve. Nowadays we call that reduction. We call that reduction to a linear programming problem. So it's the process of formulating your problem as a linear programming problem. And again, it's reduction. The solution to the linear program gives the solution to your problem. So what do you have to do? You have to identify what are the variables. You have to define the constraints, the inequalities and equations, and you have to identify and define an objective of function. That's all you have to do, though. Once you have those things, then pretty much you have a linear programming problem. And you do have to convert to standard form, but usually you can count on the software to go ahead and do that. Let's look at some examples that I've said reduced to linear programming problems, or can be modeled as linear programming problems. And we'll just use the modern term of reduction. So for example, max flow problem. So this is the max flow problem that we considered. And its input is a weighted digraph. And there's a source vertex S and a sink vertex T, and the weights indicate capacities, and what we're supposed to find out is what's the maximum flow from S to T. Doesn't seem to be that much related to linear programming, but if you just look at the idea, well, what are the variables going to be? There's going to be, and what are the constraints going to be, and what are the variables? Well, the variables are the amount of flow along each edge, and the constraints are there's got to be positive flow, and it's constrained by the capacity. So this is just a mathematical formulation of the problem. From 0 to 1, you have to have flow that's between 0 and 1. And from 0 to 2, you have to have flows between 0 and 3, and like that. So that's all saying that's what the capacity constraints are. And the other thing about the flow is that we said the inflow has to equal the outflow at every vertex. So we have a variable corresponding to the flow in each edge, and then we can just express the flow conservation constraints. The amount that comes into vertex 1, which is x01, has to equal the amount that comes out, which is x13 plus 14. And you have one of those constraints for each one of the vertices. And then what's the objective function? We want to maximize the amount of flow that goes into number 5, which is x35 plus x45. That's an LP formulation of the max flow problem. It's really, and it illustrates how really easy it is to represent a maximization problem as an LP problem. And again, you have an LP solver, you just put in those constraints. So the variables are positive. It's just all inequalities and a couple of equations. Then the software converts it to the standard form and gives you the solution. Now, it might take longer than our specialized algorithm that we looked at based on searching in the graph and so forth, which is a very wonderful algorithm and very useful in lots of applications. But the advantage of the LP formulation is that if the problem gets more complicated, say we also want to insist maybe there's costs assigned with each flow. And so we want to maximize it, but we also want to keep the cost under control. Or any kind of specialized constraint that might come up. In the LP formulation, you just add those constraints. In our other formulation, it might completely ruin our approach to the problem. That's the advantage of LP and why it's so widely used. Here's another example. This doesn't seem at all to have that much to do with linear programming, but it's the maximum cardinality bipartite matching problem that we considered, and that's matching students to jobs. And so this is we've got a bipartite graph. One set of nodes corresponds to students, the other set of nodes corresponds to jobs, and have edges corresponding to job offers. And if we want to know the maximum set of edges connecting one to another, that matches a student to a job. And we did that one by reducing it to max flow, actually. But also you can just specify it as an LP formulation of an LP problem. So it's everything's got to be 0. And it's just going to maximize, this is all the possible matchings. And then the constraints are, there has to be at most one job per person. So if A has 3 edges, just say x0 plus xa1 plus xa2 less than or equal to 1. And you do that for each person, and then at most one person per job, just do it that way. Now, this is not a trivial reduction. There was some math, quite a bit of math done early on, including von Neumann was involved. So if you have a polyhedron like this, that where the right-hand sides of the inequalities are all 1, all the extreme points of this polyhedron have integer coordinates. They're either 0 or 1. So we need that theorem, but and it's not always so lucky. But in this case, you can do it, and you can just use this linear program to solve the matching problem. Again, no specialized algorithm. Just throw in your constraints, and you have the solution. Use your LP solver. So that's just 2 examples, and there's many, many more examples. And again, as I said, you can take a problem like one that we solved and just add more things. So I want the shortest path that doesn't go through a certain node, or that only has a certain number of nodes on it, or whatever else, any other kind of constraints that you might think of. You can just throw them in. If you've got an optimization problem, One thing you can do is definitely, use an algorithm that you learned and go to the literature and try to find a solution. And that is certainly very effective for many of the fundamental problems that we've considered. But if things start to get complicated, it's really a good idea to think about using linear programming, because it's often easy to model your problem as a linear program, and you can solve it with a commercial solver or available, if it's a small one, a readily available solver. It might take a little longer than your specialized solution if you had one, but you might not care and you might not have one. And the idea is, it really is a good idea to learn to use an LP solver. Really the takeaway from this is there's a lot of problems that reduce right to linear programming. And we've got a fast way to solve it. So that's a powerful problem-solving model with broad scope. We can solve it, and we can reduce a lot of important practical problems to it, and that's why it's important. So this leads us to a really profound question that's called the PNP question. And that'll tell us, and we'll talk about this in detail in the next lecture, that there's a condition that is very fundamental to the efficiency of computation that'll tell us that people don't think that there is a universal problem-solving model. For the time being, however, and for the last 50 years, the closest thing that we have to a universal problem-solving model is linear programming.